To prove if this dice is fair using the chi-squared goodness of fit test, we, given a sample size of 100 and significance or alpha level of 0.05, we are going to need to calculate our expected outcomes and observed outcomes. The null hypothesis is also just that the die is fair, meaning each outcome is equally likely. So of the outcomes of rolling a 1, 2, 3, 4, 5, or 6, they would be equally likely. If the chance of you rolling any outcome is 1, then you rolling a given outcome in a set of 6 should be 1/6. And given our n equals 100, our 100 samples, our expected count for each outcome should be roughly 16.6 repeating, 100 over 6. Let's double check that. Yep. Obviously, we cannot have a partial outcome in this case, so there's going to be a little bit of error there, but we will round our decimals to whole numbers at the end to hopefully reduce error. Once we have our expected and observed outcomes, we can calculate our chi-squared. Our test statistic. I've already found the critical value and just done the boilerplate work, since that'll apply regardless of what our sample says, at least given our parameters that we're testing with. N equals 100, alpha level equals 0.05. Critical value should be 11.07 using this specific chi-squared distribution table. We get our critical value using by looking for the value in the table based on 1 minus our alpha level, so 0.95, and degrees of freedom of 5, because we have 6 outcomes, meaning n minus 1 equals 5. Degrees of freedom is 5. And after observing our outcomes, we will know if we have enough evidence to reject the null hypothesis that the die is fair. And not sure if I said it, but the alternative hypothesis is that the die is not fair. There is not an equal probability of rolling each of the possible outcomes. So we're going to find out if we have enough evidence for that after 100 rolls. The scratched out table is from me losing track of my rolls the first time around. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Oh, I'm gonna redo that. Roll it. Get weird. 24, I think. 25. 26. 27. 28. 29. 30. 31. 32. 33. 34. 36. No, 35. 36. 37. 38. 39. 40. 41. 42. 43. 44. 45. 46. 47. 48. 49. 50. 51. 52. 53. 54. 55. 56. 57. 58. 59. 60. 61. 62. 63. 64. 65. 66. 67. 68. 69. 70. 71. 72. 73. 74. 75. 76. 77. 78. 79. 80. Let's do a preliminary count before we're done, just to make sure I'm not off. Should be 80, I believe. So we have a total of 30, 45, 65, 75, 80. Yep, cool. We are on count, and let's keep going. 81. 82. 83. 84. 85. 86. 87. 88. 89. 90. 91. 92. 93. 94. 95. Let's do another count just to make sure I don't over-roll like last time. We have 20, 30, 50, 60, 70, 85, 88, 89. It's 95. 96. 97. 98. 99. And 100. Now we have all of our observed outcomes, and we can calculate our test statistic. My table is growing huge because I had to scratch out other data that I put in pen. So we have let's triple or quadruple check or whatever that our observed outcomes sum to 100 count-wise. Yep, they sum to 100. Let's put our expected outcome of 100 times 1/6, 16.6 repeating into variable x, just so if anything gets messed up, we can easily change it, and so I don't have to type the fraction again. Now we're just going to do the summation of observed minus expected counts, quantity squared, all over the observed, or all over the expected. Okay. Test statistic has been calculated as 9.8. A little bit on the edge there, but when we check if 9.8 is less than our critical value of 11.07, we get, or if we check if our test statistic is greater than the critical value, that is false. And thus, we do not have sufficient evidence to reject the null hypothesis of the die being fair, and thus we don't have enough evidence at the significance level to say that the die is not fair. So, for all intents and purposes, our test shows that this die within our parameters is fair, as far as we know.